Hi everyone, my name is Hui, and today I'm going to present our recent work about wearable 3D machine knitting, which can automatically generate shapes knitting sheet to cover input real-world objects. Machine knitting is a powerful mechanism for fabricating 3D shapes. Knitting machine can naturally produce curved surface directly in 3D using various shaping techniques such as show, roll, increase, and decrease. Here are recent work of knitting 3D shapes. The user can input arbitrary 3D shape, and those methods are able to automatically generate machine instructions. However, these methods do not consider the eventual assembly of the fabricated knit pieces with a target solid object. Therefore, the resulting knit pieces with this method may not be able to be placed over the targeted real-world solid object and thereby fail to fulfill their main purpose. To address this crucial problem, our goal is to give an input 3D surface and a target rigid object. Our method can automatically produce a wearable and a machinable surface. In particular, our pipeline first cuts the input 3D surface into a topological disk, while no singularity allowed in the interior of the cutting mesh. It then runs two modules in parallel, the wearability test and the machinability test. The wearability test is used to determine which edge of the air cut surface should be temporarily placed and which may be permanently sewn. Concurrently, the machinability module generates an anisotropic stitch mesh and schedules the machine knitting instructions. First, I will briefly explain how the knitting machine works. Here is the knitting machine, and in the middle shining white row are hook-shaped needles. The industrial knitting machine has hand-rotated needles next to each other in a long row. We call this a needle bed. This type of knitting machine has two beds. We call the front needle bed and back needle bed. Each needle are capable of performing four basic operations: knit, tuck, transfer, and split. The entire back bed can slide to make the transfer operation become more useful. And here is one example that we can knit a loop and transfer one loop to the back bed and the slack and transfer back to form a decrease stitches. And with those four basic knit operations and ranks, we can knit various knitting patterns shown here. More importantly, use a shaping technique such as increase, decrease, and show roll. Knitting machine can produce non-developed surface directly, which is a clear advantage to traditional cut and sew methods. Our method is based on stitch mesh framework, in which an interlock yarn structure is represented as a stitch mesh face. Based on the yarn connection along the edge, we can define top cross edge, bottom cross edge, and wheel edge. Tiling stitch mesh face can create a stitch mesh patch, which also has a cross direction, wheel direction along the patch. In other words, we can define a twofold rotationally symmetric cross field on the surface based on the wheel and the cross edge. It is relatively straightforward to tell the stitch mesh faces for simple mesh without any singularity. However, for complex mesh surface, if there exists any directional singularity as shown here, and it will cause a lot of small closed loops which are not machinable. Or if we have the edge with one side cross edge, another is wheel edge, will cause a broken yarn, which is not machinable either. Another problem will prevent machinable is the needle overlapping. On the left, we have a garment flattened into 2D with two knitted pieces, B and C, connected with A. On the right, the needle time bed view for the knitting the garment, which shows which needle are holding those at which point during the construction time. The primary challenge faced by any scheduling algorithm is that those stacked on the same needle at the same time can never be separated. If C is knitted before B, and loop holes for B interfere with the needle needed by C, which will cause a problem. This can be resolved by shifting C one needle per row to make it knittable. However, local shifting will cause a large local dragging force and potentially unstable. However, if we can knit it in the right order, in particular, for example, if we knit B and first, then C, there will no needle overlapping problem. So when determining the knitting order, we need to find the right order to avoid needle overlapping, so to make the machine knittable. This is the key problem we try to solve in these papers. Our pipeline starts with surface cutting. We first cut the input 3D surface into a top rock disk, and no singularities are allowed in the interior of the cutting mesh. The input surface is first converted into a cross-dominant proxy mesh from which a cross field can be derived. Then we use the patch gluing algorithm and extend to deal with singularities. The algorithm begins with forming a patch with arbitrary seed chord, and the edge of which are labeled with the field direction, and groups it one seed at a time. Specifically, each grouping step consists of 3 steps. First, edge selection, random pick any one edge that neighbors a non-weighted face. Then expansion attach the face into the patch over the selected edge. Edge labels are propagated consistently to attached face. Last, fusion remove the pair of edges if they have same labels and on the opposite side of the same edge. And we don't have that pair edge here, so that keeping select the edge and the expansion, the edge and expansion until here we find there have one edge have paired the same type of edge. Then we can do the fusion to merge them together. Then we can keep into the edge selection, green, good. Until we reach here, then we have one edge, the two sides are different types. Then we cannot handle that because it is not machinable, so our solution is just cut them. And here is a real example that the facility mode after cutting. All color edges here are cutting edge. We also show the flattened cut surface in proxy parametric space on the top right. Apparently, some sequence of boundary edges are zigzagging, which is not friendly for knitting and does not look like Wearable either. Also, the patch overlapping will cause some needle overlapping when we do the scheduling, so additional cut may be required to solve that overlapping. To further improve the cut selection, we first improve the cutting straightness by discouraging the sequence of boundary edges that are zigzagging. To achieve this, first our system identifies the irregular vertices. From each irregular vertex, expel n particles called motorcycles, one along each edge. A motorcycle travels across the edge in a topologically strange fashion until it reaches the vertex that is previously visited by another motorcycle or is on the boundary of the mesh. When motorcycle reach a vanishing corner of a triangle, it randomly picks out one of two possible strange edges. Finally, assign higher cutability score to the strange sequence of the edge. And to reduce the possibility of a 2D overlapping, we first estimate the parametric 2D position of the face, and then we can compute overlapping count for expansion move. Then we can assign lower cutability score to the move with more overlapping faces. And here's the comparison. If randomly selecting the expansion move, as mentioned before, the output result has zigzagging boundary and overlapping in the parametric space. By comparing these two conditions we added, our result could produce a better cutting result, have more straight edge and fewer overlapping as shown on the right. Once we have the cutting mesh which does not have any similarity in the material, we can convert it to a stitch mesh and generate the knitting instructions. Given the stitch mesh as shown on the right, our system first groups all faces into rows, where each row contains the faces that are placed side by side along the course direction. These rows are viewed as a graph, where each node corresponds to a row, as edges are induced by connection between rows. Graph paths are removed if removing would not lead to disconnect graph. Finally, auxiliary chains can be collapsed, resulting in a desired graph grouping. Now we need to determine the order of grouping phases. Based on the knitting dependency, we can see the patch graphs are acyclic directed graphs, and the open knitting order must obey the knitting dependency. Unfortunately, as they are most resource scheduling problem, it is impossible to find globally optimal solution in practice, given the potential space of the knitting order. Here we show a few number of the potential knitting orders on the right. So our solution is to test a fixed number of random generated knitting orders. And for each knitting order, our system performs a knitting simulation on the needle bed to identify overlapping. When an overlap is detected, the system will introduce a cut between the connected patch, as shown here. And after testing a fixed number of users specify the knitting order, system pick one that introduces a small number of cuts. Then we'll guarantee that given a computational budget, our method will always return a machine-knittable solution. So far, our system has identified a set of cuts which make the garment knittable. And in this stage, our system ensures the viability of cutting surface while removing as many cuts as possible. And the goal of this stage is to remove as many cuts as possible while ensuring the viability. Our strategy is to remove one cut at a time and reinsert it if the resulting design is not viable. Each cut will be tested once and marked for the permanent sewing. It can be successfully removed in the process. To quickly determine whether or not the given design is wearable, our system uses physical-based simulation of the process of wearing the garment. Instead of searching for strategies that to put on the garment, our system follows strategy to check if the garment can be stripped off by a set of simple external force, starting from a configuration where it is already on the given object. Two types of the external stripping force are used. Local force repels the garment away from the wearer. Our method applies a force to each garment mass based on the direction of the gradient of the assigned distance field. And we also add the global force of the continued magnitude to drag all the garment mass in an arbitrary direction, which is changed randomly every fixed number of simulation steps. And here is one example that we to test all the cut edge. It can be either success or failed. And if it failed, we will keep that cutting edge. And here's the final result we can show here. And here showing another real garment being removed from following the wearability simulation. And here we'll talk about more results. On the left, the facility model with yarn texture, yellow edge are cut that are sewn permanently, and red are indicated listed edge. On the right, the real knitting garment on 3D print model and the seam knitted by the flattened garment is shown on the top right. Notice the local curvature of the flattened garment, which are introduced by the knitting shaping technique. And here we show another physical reliable example, the rope arm model. Observe how the garment can reproduce the shape of a fixed model, introduce strong concave regions. And the garment mesh does not doesn't need to follow the target match closely. For example, we use our system to produce both tight-fitting sweater and a loose skirt for the center model. So in conclusion, we introduce a complete system that put all together to guarantee both machinability and wearability for 3D machine design, and that including an automatic cutting algorithm, anisotropic stitch meshing technique, stochastic anytime scheduler, and constructive wearability test. So in order to get more detail, please read our paper. So thanks for watching.